Okay, I always like to do a little pre-lecture before the real lecture, give you more than your money's worth. And what I got up there on the screen is the Eye of Horus. And the great neuroanatomists of the ancient world were the Egyptians. Bad news, people forgot how to read hieroglyphics. So all that they wrote about anatomy was pretty much lost until the 1800s. The only thing we got left from the Egyptians, you ever see this symbol? That's the Eye of Horus. That's the only thing that's left in our modern medicine. So that's where that comes from. RX doesn't mean anything in Latin. But I'll talk to you a little bit later about what we do have left from the ancient world and why we still talk in Greek and Latin. All right. So here's a plate from one of my favorite people in all times. This is from Vesalius. He was about 15. This was about 1543, and he is considered the father of modern anatomy. And so what he started doing was actually he started doing human dissections again, and they hadn't been done for a long, long time. In fact, most of the Greco-Roman times they were outlawed, and then the Catholic Church took up and outlawed human dissection. Actually, Vesalius was breaking the law when he did it. And so they would actually, the Pope would get, he was up in Padua, the Pope would get word that Vesalius is doing human dissection, so he'd like, all right, go up there and see what he's up to. So, of course, they would see some guy coming into Padua, and they say, run in there, Vesalius, the Grand Inquisitor is coming. So Vesalius would run to a church, confess his sins. When the Grand Inquisitor gets there, he's like, the guy was in a state of grace, couldn't do anything to him. Goes back to Rome. Vesalius, next corpse, starts doing more human dissections. But that wasn't until the 1500s. And so from ancient times till the 1500s, the only thing that was still around that people could read, because we couldn't read the hieroglyphics anymore, was in Greek and Latin. Okay? And so to this very day, what we still have is a lot of Greek and Latin in anatomy. And I grew up in a remote island in the Mediterranean, and we spoke Latin at home, but I understand that's very rare. Most of you probably didn't speak Latin at home. And so I'm going to try to get you through this. So a few things that we're going to be using, some prefixes. Peri means around. Okay, so perimeter actually means to measure around. We'll be looking at a structure called the periaqueductal gray. Okay, para means beside. Okay, so paramedics work beside the doctors. We'll be talking in lab about the paraventricular nucleus. It's the nucleus that's beside the third ventricle. Hypo means below. Hypodermic means below the skin. Hypothalamus, below the thalamus. Pre means in front of. You've probably already heard of the precentral gyrus. We'll be seeing this in lab. Y'all hear these things? Yep. Okay. Post means behind. Post-central gyrus. And then there's also something we'll be using called superior. Also super or supra means above. So here today in this lecture I'll be talking about the superior colliculus. And so also Dr. Krasny will be using a term supra-threshold. That means above threshold for an action potential. Inferior doesn't mean it sucks. Infra just means below. So we have things like the inferior colliculus below the superior colliculus. Epi means on top of. Epiglottis is the thing. Epi means on top of. Glottis is tongue, that thing that hangs down from your tongue. We'll be seeing a little bit of the epithalamus. And something I'll be turning to here shortly today is ipsi. Ipsi means same. So if it's ipsilateral, stays on the same side. Contra means opposite. If it goes contralateral, be on the opposite side. Okay. What we're going to turn now to is talk about some basic directions in anatomy. And so I have my friendly fish here to help us out. All vertebrates are laid out like this. And So if it's toward the stomach of the person or animal, it's said to be ventral. So ventral is towards the stomach of the person or animal. Okay, that's ventral. Okay, you drinking coffee there? No? A lot of caffeine? All right. Dorsal, in contrast, is towards the back of the person or animal. I want to make sure you have a steady hand because you're going to stick this on my back. All right. So dorsal is on the back of the person or animal, and ventral's towards the front of the person or animal. Got it? All right. So all that's well and good, but as I said, for a long time, human dissection was forbidden. All right, so they worked out all these directions on four-footed beasties. And a four-footed beastie, I've got to be a four-footed beastie here for a moment. All right, so four-footed beastie here, dorsal toward the back, and dorsal on my head is this way, okay? And ventral is here, and ventral on my head is this way. Well, we're not four-footed beasties, and our heads are ventriflexed. Okay, flexed up towards our tummy. So on the human, dorsal is this way on the head, okay? And ventral on the head is going down like this, all right? So ventral's that way. Ventral's going down. My beard, I think I got a slide here. Yeah, here, all right. So my beard is the ventralmost part of my head. Dorsal is the top of my head, okay? So the head's different from the rest of the body. Let's go back to my fish here. All right. So we've got a three-dimensional person or animal, so we're going to need three axes to specify them. So we're going to need another axis that is medial and lateral. So medial means towards the midline of the person or animal. Would you be so kind as to append this sign to that one that's there? Thank you. Okay, medial is towards the midline of the person or animal. And dentists, for reasons I don't know, say mesial, but it's the same thing. So if you turn into dentist, can you come back and tell me why? All right, so mesial, medial, same thing, towards the midline of the person or animal. And then lateral, any Bruin football fans? How are we doing this year anyway? Good? Good. Undefeated. We're doing very well. All right, lateral, which way does a lateral pass go? Can you append this? Huh? Sideways. Laterals to the side. Okay. So laterals to the side, mesials to the midline. Thank you. All right, so we got two axes, and so now what we're going to need is a third axis, and the third axis actually has two names. So one is anterior, posterior. Okay, so anterior is towards the front of the person or animal, and then posterior is towards the hind end of the person or animal, and I'm going to give you the pleasure of pinning this to my butt. All right. All right. Anterior toward the front end, and posterior towards the hind end. All right. Thanks. Okay. Anterior and posterior have another name, and I'm probably more likely to say those just out of habit, and that is rostral and caudal. Rostral means towards the nose of the person or animal. So rostral is towards the nose of the person. Rostral rhymes with nostril, so it's towards the person, nose of the person or animal. And then caudal is toward the tail of the person or animal. Would you be so kind to attach my tail? All right, so rostral towards the nose, caudal towards the tail. All right, same as anterior and posterior. Okay, so got it? All right, so now let's do a little quiz. If I were to ask you, where is the tip of your nose relative to your eyes, what would you tell me? Rostral by definition. What else? Anterior, what else? Medial, what else? Ventral. Okay, so it's ventral, medial, rostral to your eyes. Got it? Okay, so you can describe where something is relative to something else using these directions. Okay, good. All right, I don't think we need that. All right, so we also have the standard planes of dissection. And at some point in our dissections, we will be doing all three of these planes. So one of these planes is called the coronal plane. Corona, actually, anybody speak Spanish? What's corona? It's not a beer. What's on the beer? Crown. That's what it is. It's a crown. Okay. Okay, so corona means crown. And the reason why this is called the corona, this kind of a cut is a coronal plane. I can't get that crown on. We'll use this crown. It was in the same plane as the Greco-Roman crowns. Okay, so the Greeks and Romans didn't wear crowns like that poofy thing that Queen Elizabeth wears. Go up to the Getty, you can see what a Greco-Roman crown looks like. Looks something like this. Okay, so that's called the coronal plane or the transverse plane, or it's also called the frontal section. And I have here to help me get these points across the cabbage heads of science. All right, so what we're going to do with this cabbage head is we're going to cut this cabbage head in the coronal plane. So let's see if I can do that. It's a lot more work than it ought to be. All right, so essentially what I'm doing to get this cabbage head cut in the coronal plane is cut his face off. All right, so this cabbage head got cut in the coronal plane. Okay? Other planes of sections. Here you can see a sagittal section, and we're going to cut this cabbage head in the sagittal plane. I just stuck my knife in the sagittal plane. So this people don't like this for some reason. All right, so this is the sagittal plane that we've stuck this knife in this cabbage. It's just a cabbage head. All right. Anybody bring a wok? No? All right. No lunch. All right, so we're going to cut this, hopefully. Okay, excellent. All right. So we did this in a sagittal section. If we're right spot on the midline, it's a mid-sagittal cut. All right? Or if we're off the midline, sometimes called parasagittal, beside the sagittal plane. All right. And then lastly, our final plane of dissection is the horizontal plane. And here I've stuck this knife in the horizontal plane of this cabbage head. And so we're going to cut basically eyes through to ears, and that's the horizontal plane. And as I said, we're going to be doing all of these cuts. You'll each get your very own sheep brain to play with. And we're going to be doing all these cuts in lab. All right. Great. Okay, so this one got cut in the horizontal plane. All right, so those are the standard planes of dissection. Okay, a little bit more nomenclature I want to introduce you to, and that is the major subdivisions of the brain. So when people in neuroanatomy and neuroscience in general are talking, we often will say things, well, this is in the mesencephalic tegmentum. If somebody says that to me, I know just about where it is, okay? So what we do is we use these subdivisions of the brain. This slide is just to show you where these things come from. This slide has way too many labels. Don't worry about it. Okay? But where these subdivisions of the brain, where do they come about? You probably already know that we develop as a neural tube. And this neural tube, in the course of development, has these outpouchings. And so these subdivisions of the brain come from these outpouchings of this neural tube. And so going rostral to caudal, which means what? Nose to tail. They are the telencephalon, the diencephalon, the mesencephalon, metencephalon, myencephalon. Is that too fast? Don't worry, it's on the next slide. All right, so But I just want you to know that's where it comes from. It comes from development. It's not some weird scheme that somebody dreamed up. I like this slide because it actually has a lot of information. Most of it is correct. There's a couple tiny mistakes in it that I'll address here in a moment. So once again, going rostral to caudal in this. The rostralmost subdivision is the telencephalon. And things that you already have heard about that are in the telencephalon, everything that's cortex is in the telencephalon. Okay? You all have heard about the basal ganglia, I presume. Yes? All right. All the basal ganglia in the telencephalon. All right, here's one of the tiny errors in this slide. Most of the limbic system is in the telencephalon. So things you probably hope you've heard about: hippocampus, amygdala, fornix, septal nuclei. Hear about any of these goodies? Okay, all of those are in the telencephalon. There are a couple pieces of limbic system that actually are in the diencephalon, but we'll get back to that. Okay, the next, going now more caudal, the next subdivision of the brain is the diencephalon, and the big deal players that you've heard about in the diencephalon are the thalamus and the hypothalamus. Okay, down in the mesencephalon, which translates directly into midbrain, but I really prefer you learn the Greek. Don't give me the English, because it's still used. Okay, in the mesencephalon, we'll see the tectum, which is Latin for roof. And the tectum is composed of the superior and inferior colliculus. Have you talked about these structures in other classes? Some say yes, some say I don't know. All right, so superior and inferior colliculus, we'll be seeing those in lab. And also the tegmentum. Down in the metencephalon, big deal players we see are the cerebellum, which I presume you've talked about. Yep. And the pons. And then in the myelencephalon, there's the medulla or medulla oblongata. That's all the same thing. All right, yes? Most of the limbic system's in the telencephalon. There's some pieces in the diencephalon, but I'll sort that out when we do limbic system. Okay, so one of the things I'm going to ask you on exams is to throw a pin in a structure. I'll say, what the heck is this? How is it connected? What does it do? What subdivision is it in? Okay, so that's one piece of information that I'll expect you to know. All right. All right, what I'm going to do with the lectures is try to give you a forest in which to put all these trees. So what I'm going to do in lectures is talk about systems. And in lab, just because of how we're going to do our dissections and the way the brain is in fact built, we're probably going to see bits and pieces of systems at different points. Okay? So I'm going to talk about these systems and try to give you some structure into which to put all the things we see in lab, which we'll probably see in bits and pieces, literally. All right, so I'm going to start out first by talking about the visual system, and it turns out we got two of them. And the one that you probably have already studied, at least I hope so, is called the retinogeniculocalcarine pathway, and we'll unpack later why it gets that name. All right, so let's start out, first of all, it starts in the retina, and let's talk about how these axons of the optic nerve course as they come out of the retina. You can see here, actually what I'm going to do is, let's say, first of all, what kind of sections are we looking at here before we get going any further? I gave you, say, coronal, sagittal, horizontal. What is this, essentially? It's horizontal, so we're looking at the person cut like this. All right, so let's say, and the person is looking up like that, and let's follow the axons that are coding for what's going on in the person's left visual field. All right, so let's start like that, and then it's the right visual field is just the opposite. Okay. So what you can see is the left visual field in this person's right eye, due to this pinhole camera effect, is going to be over on the right side of this retina, okay? And in the left eye, it's also going to be on the right side of the retina. Check? All right, good. You got an A in physics, I could tell. All right, so let's see what happens. So if these axons are coming from the lateral side of the retina, what they're going to do is they're going to stay ipsilateral. What's that mean? Same side. Okay, they're going to stay ipsilateral before they synapse. Okay? In contrast, those axons that are coming from the medial side of the retina are going to course contralateral. They're going to go over to the opposite side before they synapse. All right? Okay. So now, when they cross, everything in anatomy gets a name. All right, so it's the optic nerve until we get to this structure here where some of these axons cross. And what's the Greek letter X? Chi. This is the chiasm. All right, because it's an X. All right, so they cross here, and then after the chiasm, same axons now are going to get yet a third name. It's called the optic tract. Okay, so before the chiasm, optic nerve, then chiasm, optic tract. All right, so unfortunately, same set of axons are going to get 3 different names. Sorry, they didn't ask me when they did this. All right, so by the time we get into the optic tract, the axons here are taking information. So we have what kind of information? So if I said, what visual field is being represented by these axons here? Left. So the visual fields have segregated, even at that point. Make sense? So these axons are coding for stuff in the left visual field, and these axons are coding for stuff in the right visual field. Check? All right. First synapse in this system is going to be in the lateral geniculate nucleus, or as it's said in this slide, lateral geniculate bodies, same thing. Lateral geniculate nucleus, lateral geniculate bodies are the same thing. It's a thalamic nucleus. It's part of the thalamus. If it's part of the thalamus, what subdivision is it in? Diencephalon, correct. These neurons of this lateral geniculate nucleus will send their axons in turn up to the cortex, and they are going to terminate. This is now a sagittal view right along this calcarine fissure. This calcarine fissure. That's why it's called the retinogeniculocalcarine pathway. And let's go and look at what we can see in the sheep. Okay, so before we go on, what view of the sheep brain is this? So this is actually the ventral view. All right, we're looking at the bottom of the sheep's brain. So this has been lifted out, and we're looking at the bottom. All right? Okay, so what we can see there, here is the optic nerves. The eyes would have been about out here. So here's the optic nerve, and then we'll be able to see the optic chiasm in lab, and then the optic tract. And we'll see that next week in lab. And then when we start doing the sections, at some point we'll be doing coronal sections. So this is a coronal section like this through, and this is just slightly back from the middle of the telencephalon, and there you can see this big white streak along the side of the brainstem. Why is this white? Say it loud. Myelinated axons, right. Okay, so big white streak is the optic tract. You can see a little bit of the lateral geniculate nucleus there, and then you're going to get a really great view of it as we go way back. This is cut pretty far back in the telencephalon. This is the brain stem. So don't let me confuse you. This is the lateral geniculate nucleus, and it's in what subdivision? Diencephalon, because it's part of the what? Thalamus. All right, so the LGN, the lateral geniculate nucleus, is going to be this huge, big, easy to spot gray streak. For reference, you can see the hippocampus near it. Okay? So that's where the first synapse is in this system. And I'm going to turn to my humans, which are a little more obvious. And then the second synapse goes from the LGN out to this area 17. And what I've got up here is what are called Brodmann's areas. Have you ever heard of Brodmann? Okay, so Brodmann, what he did was he cut through the whole cortex. And every time the cells looked different, he gave it a different number. And the good news for us is oftentimes that corresponds to function. So here on the lateral surface, which would be like out here, the very tippy end of the occipital lobe is area 17. That's where those axons terminate from the lateral geniculate nucleus. So I might stick a pin in there and say, this gets projections from where? That means, let me slow that down. If I say, if this gets projections from where, I'm saying, this gets axons from where? Axonal projections from where? It gets axons from where? All right. So if I stuck a pin in area 17, or this, which is also known as the striate cortex, or you may also have heard it called V1. That's a physiologist kind of thing. If I stick a pin in there and I say, this gets projections from where? What would you tell me? LGN. Okay. And here, this is a sagittal view of a human brain, and this is that calcarine fissure. And you can see that area 17 makes the lips. These gyri make the lips of this fissure. So all of this gets projections from the LGN. Okay, so let's do a couple of visual problems. There are very few but interesting cases where people have gotten their striate cortex selectively destroyed, wiped out. All right? And so they have no conscious visual perception. You talk to them, they tell you they're blind. All right? But if you were to do something like you stick an obstacle in their path, they step around it. Okay? So people got interested in because these people act like they can still see, even though they said, nope, completely blind. So they gave them a test. Are you guys too young to have ever seen Pong? Yes, I take it you are. All right. It was the first video game out. It was so cool. It was a little ball that went bouncing around a screen. Okay? So what they did was they basically got this Pong screen, this little ball bouncing around the screen, and they take one of these subjects up, and they say, okay, so put your finger on the thing that's moving and keep it in. I can't see anything. I'm blind. Well, if there were something there, put your finger on it. They can stay on target 70% of the time. Okay, so clearly they can have visually guided behavior without any conscious vision. It's a phenomenon called blind sight. Okay, blind sight. Why does it work? One theory, not without controversy, but one theory is because we have two visual pathways. They have one screwed up, but one still intact. All right? So, tectofugal visual pathway. Fugae means to fugitives, run away, right? So this is going to run away from the tectum, which is, in this case, superior colliculus. Tectofugal. All right? So, it doesn't get a lot of press, so I couldn't get a lot of beautiful images to show you. But it starts both retinas, and their first synapse is in the superior colliculus. And I'm going to blow my next question. What subdivision of the brain is it in? Mesencephalon. All right. Superior colliculus projects to. When I say projects to, what do I mean? Sends axons. Sends axons to the pulvinar nucleus of the thalamus, which is in what subdivision? Blew that one too. All right, so that's in the diencephalon. And then that thalamic nucleus will send axons or send projections to the extrastriate cortex, which are Brodmann's areas 18 and 19, and physiologists call them V2, V3, which you also, anybody have Dr. Shine? Yes, so you probably heard all about this good stuff, right? All right. Everybody done with this slide so I can go on? Yes? No? Yes? No? All right. All right. Okay, this is the best I can do by way of a beautiful picture. So what we got here is a brain. The person's facing sort of into the screen. This is kind of a see-through brain, so this ball here represents the thalamus. Here, these bumps represent the superior colliculus. So the way this thing works is it goes from the retinas. First synapse is in the superior colliculus. Second synapse in this real purple area, that's the pulvinar right next to it. And then the pulvinar sends axons out to the extrastriate cortex. Some people think this system is also involved in health, in attention. We're going to get one view of the pulvinar. This is a horizontal cut of the sheep brain going eyes through ears. So one of the very last things we'll do, you'll actually get to see the pulvinar. Sits right next to, this is the LGN out here. And the pulvinar sits just medial to it. So we'll get to see that. And then this pathway, this tectofugal pathway, ends up in areas 18, 19, which is also V2 or V3, and anatomists call it the extrastriate cortex, outside the striate cortex. All right, let me give you another problem in vision. Let's go back. Okay, let's go back to this first slide. Now, pituitary actually sits right in back of this chiasm. Okay? So let's say, can I show you a pituitary? I think so. Yeah. All right, so this is the pituitary gland, and this infundibulum is part of it. So it sits right in back of this chiasm. So let's say somebody gets a pituitary tumor. Okay? It's going to compress these axons of the chiasm. They're going to get unhappy and stop working. What will the symptoms be? You'll get tunnel vision, okay? Because the parts that cross over are the parts that are on the medial side, right, of your retinas. So that's looking out here. That's getting the information from out here, right? They all die. All right, so all you can see is just this part. Okay, make sense? Okay, I might ask you questions like that too. Those are kind of fun. All right, do I have time? Oh yeah, we'll do a blitz here. Okay, quick. We're going to do one quick thing about the auditory pathway, and that's to tell you about problems in hearing. All right? So, most of the auditory pathway, actually the auditory pathway is both crossed and uncrossed. Okay, so some of it goes contralateral, but some will stay ipsilateral. All right? That's true for most of it. Accordingly, most places, if you get damage to the auditory pathway, you get hearing loss in both ears. Does that make sense? Because you have both crossed and uncrossed. All right, so if something gets blasted, you're going to blast both the crossed and uncrossed aspects. There are a couple places where you can get unilateral damage. All right, and the only place that is actually is in the cochlea. You all learned about cochlea, right, in 116. I don't have to talk about cochlea being the organ of hearing. Good. All right. 115. So the cochlea gets damaged, you can get unilateral hearing loss. And also, the first synapse in this system is either in the ventral or dorsal cochlear nucleus. If those get damaged, you can get unilateral hearing loss. Anywhere else, you'll get bilateral. Okay? Cochlea itself or the first synapse, unilateral. Otherwise, bilateral. Okay. I have bilateral hearing loss. Sometimes I'll say, yell at me, I can't understand you. All right. So, where do I have damage? You know how I did it? I used to love to listen to rock and roll music cranked up with headphones on, really loud, all right? And you know what? My stereo had to be plugged into the wall when I was doing that. I couldn't walk around with it. So I'm going to give you that warning. If you want to be my age and still have good hearing, don't crank it up. All right, and so with that thought, I will leave you for today, and I'll see you in lab.